UC Berkeley and later on postdoc in UC Berkeley and also in Stanford. So she and her team actually have been focusing on domain adaptation, transfer learning, learning with auxiliary tasks like over many years. So I mean, today we are so happy to have her to share some of their recent work. So yeah, I mean, yeah, so now time is yours. So yeah, go ahead, Judy.
Great. Thank you. Thanks to the organizers for inviting me to this workshop. So today I'm going to talk about reliable and reusable vision. And what I mean by that is I'm going to talk about ways in which we can understand whether or not our vision systems are going to work across a variety of appearance scenarios, a variety of environmental scenarios, and then also find ways in which we can reuse components of vision systems that were created for one purpose and retask them for another purpose. So to understand that, first we have to start by just thinking about the standard learning pipeline that we all know. So when we're talking about visual recognition, the canonical pipeline that we all use is we start by collecting some amount of data. We need to curate it and annotate it if we're doing supervised learning. And then we're going to train a model. And the model's job is just to be able to predict these labels that we've annotated for it. And finally, we get to this validation step. And this validation step is what we use to convince ourselves that the model that we've trained is really generalizable. It's going to work well as we deploy it. But of course, this piece, this validation step, tends to be a bit flawed if our goal is to take a system trained in a static set of data and then deploy it into an open world. And to understand that, we can start digging into what happens when we take a model that was trained under some set of circumstances and try to deploy it in maybe just a slightly different set of circumstances. So for example, we think about the ImageNet benchmark challenge. This challenge has a lot of diversity. It has a lot of classes that you need to be able to recognize, millions of images. And naturally, we measure performance on benchmarks such as this over time and find that our performance is improving. And a lot of the improvements that we're seeing in this challenge had to do with increasing the size of our models and having sufficient compute to be able to train them. Once we got to this point where we had this model, this is going to be a large ResNet model for the purpose of winning that challenge. And now there's newer architectures that are performing even better on this challenge as well as others. But the thing is that when you take this model, this large ResNet that was working very well on recognition on a held out test set from this ImageNet data set, and then you try to use it to recognize categories that already appear in ImageNet. So ImageNet has, again, 1,000 categories. It has annotations, it has recognition capabilities for concepts like dogs or different dog breeds. But if we ask it to be able to recognize a dog in a similar scenario, at least a scenario that seems like it should be very similar from a human perspective, like recognizing this dog in a YouTube video, we find out that our model is not capable of recognizing this dog, despite the fact that it could recognize dogs very efficiently as validated in the ImageNet test set. So this brings us to the problem of dataset bias. And when we're talking about dataset bias, what we mean is that no matter the size of the data set, if there is a curation, a capture, or any other kind of bias to the process with which the data is collected or annotated, that bias is going to be encoded in our model. And so when that bias changes, when the situation changes, when the way in which we're collecting data or using data changes, the efficiency of that model is going to degrade. So here we have some example images of dogs from ImageNet. And when we're talking about dogs in ImageNet, these dogs are going to be images that people decided to share with one another. And they shared with one another in a static image medium, so just a single image, things like Flickr. So when you think about the kinds of images that you want to share with your friends and family or with a photography group, it's going to be, in the case of dogs, it's going to very frequently have things like the face of the dog. It's going to have the dog in the center of the frame. It's going to tends to be higher resolution and nice lighting conditions. But when you think about the types of videos that you share on YouTube, we find that maybe you are selecting for an interesting action, maybe because it's transient, you don't have time to take the video multiple times and pick the best video. And so as a result, you might have artifacts like lower resolution, motion blur, and a wider variety of poses. So these still frames have a very different appearance than the images that we saw in a data set that was collected from curation on static image data sets. If we move on to some other tasks like semantic segmentation and driving scenes, and we think about all of the diversity that could occur in these scenes, it's natural that because it's so expensive to annotate for a task like segmentation, in fact, it can cost between $10 to $12 just per single frame. And then we think about the kinds of variations that appear in this particular task, like changes in weather, changes in the city that you're operating in, changes for the sensors on the car. So when you think about the set of possible sources of variation, it becomes intractable to think about annotating all possible factors of variation. And so any static set of images are going to have one particular distribution over these factors that may not match what you see at deployment time. And we can try to analyze how much our systems might fail if this happens by setting up simple experiments, like asking if we were to train in primarily sunny weather conditions, like this image here, and then we wanted to know how well our system would work if there was snow on the ground. Well, it turns out that the system that was trained in sunny weather conditions would fail pretty miserably when there was snow on the ground. And in fact, it especially failed exactly like you would expect on the road and on the sidewalk that have snow in this particular scene. And then lastly, there have been a lot of studies that look at general robustness of vision systems. So the changes don't have to be something as systemic as center cropping or weather changes or city changes. It can be even small artifacts that appear in an image. So in this work, they studied how much a system would degrade if a new type of corruption appeared in images. And that could be a corruption like the blur I was showing before, but it could also be corruptions that have to do with compression artifacts or just noise in images or changes in lighting conditions. So one question we had was, well, if we are trying to understand the impact of degradation in vision systems, what happens when we are using vision as a component of a larger system? So rather than just doing visual recognition by itself, what happens if we have some amount of corruptions to our visual inputs and we're using this as input to another task like visual navigation for embodied agents? And for that, we created this benchmark called RobustNav that was presented just earlier this week, where we tried to study just this. We tried to create a system that allowed you to analyze performance degradation for embodied navigation. So tasks like point nav and object nav, this is going to be in a simulated environment where the agent is asked to navigate to either a particular location or to a particular object. Obviously, in the case of navigating to an object, you need to be able to solve a navigation task as well as a recognition task. In the case of point nav, you still need to be able to take as input the visuals of a particular scene and decide what action to take. So you'll see scenes like this. You're given an RGB image. Maybe you have an additional sensor like a depth sensor. And the agent's goal is to be able to choose between a set of actions in order to navigate to the desired point or the desired object. And here's an example of an agent moving around in the scene to arrive at the correct object. Okay, so to design this benchmark, we investigated primarily corruptions to the vision system, but we also integrated some corruptions to the dynamic system, very simple corruptions. We have 7 visual corruptions in total, and these look like this, where we have taken some from the original Dan Hendricks paper, but we also integrated some new corruptions that were more applicable to the embodied agent scenario, like spatter, which was emulating having some amount of debris on the camera, or camera crack, again, emulating there being some sort of deficiency in the capture system. For dynamics corruptions, we had 4 different corruptions, 2 of which emulated different environmental conditions, especially having to do with friction. So things like if the floor were to become higher friction or lower friction, so more slippery or less slippery, then what would happen is when you tell the agent to move in a particular way, it's not necessarily going to follow that exact instruction the way that you would have expected during training time. And the other 2 corruptions have to do with faulty components in the robot itself. So things like if you had a malfunctioning motor or a wheel, and you asked the agent to move forward and it didn't necessarily move forward in exactly the same amount as you would expect, or you asked it to turn and it turned normally in training time, it turned 25 degrees and now it only turns 15 degrees, things like that. So we're asking, essentially, as we're doing this visual navigation task, what happens if some of the conditions at test time deviate from how they were at training time? And probably unsurprisingly, what we found was that in the scenario where an agent is able to navigate when both the vision system and the dynamic system match the way it was trained, it's able to solve the task. But as conditions start changing, so lighting is, in this case, it's a lower lighting condition. The agent is now struggling to be able to recognize the object it's searching for, and so it actually walks past it multiple times before it stops. It does eventually find it, but with other corruptions, it's actually unsuccessful entirely. It can't ever find the object, so it's just kind of navigating around this environment over and over again, looking for this object that it's asked to find. So we come back to this idea of environments changing at deployment time or at test time. A natural question to ask is, well, if things are changing, why would we expect this system to continue to work? And why don't we just collect some more annotations and solve a new task that matches our new scenario? And that's a pretty natural question, but of course, collection of annotations is really expensive. Not only is it expensive to acquire these different kinds of annotation, and there have been a whole industry that has arisen to solve some of these tasks, but it's also just expensive to be able to, and both in time and money, to be able to curate a new data set and determine what are the factors that you need in this new setting to be able to successfully annotate the diversity that you need to have a system, a supervised system that works well out of the box in your new scenario. And sometimes it's not even feasible at all. Sometimes things change all the time, especially in that driving example. You're going to have cars in multiple different scenes at all times, and there may be new appearances that arise over time. And so we can't necessarily always rely on having a static data set that we curate, annotate, and train a new model to match our new conditions. So instead, we look at the task of domain adaptation, which means that we're trying to understand what pieces of a model that was trained under one set of conditions can be reused under another set of conditions. So more formally, what we have access to is a large labeled data set this is what we call our source domain. So this is your original data set. You've already curated it and annotated it. You've trained a model. You've measured your validation curve. You know that it works well if conditions match your training conditions. So things like that original ImageNet data set, we know that we have a model that works well at performing this task. You might have annotated images taken from, let's say, a product warehouse or somewhere where you already know the types of products that you want to recognize. And your annotated data might just come from simulation. So it might be you're trying to solve this driving task, and in order to visualize all of these different factors of variation, we can enumerate them and simulate different images that have the variety of weather patterns, the different cities, the different appearance of the scenes. But then, of course, for all of these scenarios, when we'd actually like to deploy our model, things are still going to change. So maybe we trained on ImageNet, and now we want to recognize in some videos. Or maybe we trained our model to recognize these products, but we want to be able to actually recognize the products as they appear when people snap a photo of them with their phone in a non-canonical background type scenario. Or maybe what happens is we just want to take our model that was trained in simulation and we want to be able to recognize similar scenes as they appear naturally in the real world. In any of these cases, the idea is that where we want to deploy our system may not have access to lots and lots of labels. So we can't necessarily rely directly on training a new supervised learning task. And instead, we'd like to be able to transfer what we know about the large labeled data set for reuse in the sparsely labeled or even unlabeled target data set. And a really common approach that people take is called domain adversarial adaptation. And if you're familiar with GANs, it has a really similar learning objective. And what we do here is we imagine that you train your source model. And because in the source data set, you have lots of labels, we know that we can train a strong classifier for data with this particular appearance characteristics. But then, of course, the problem is when some factors of variation change, like when we're trying to take a model trained on product warehouse images and then recognize those products in the wild. What we discover is that the distribution of features between these two scenarios is not necessarily aligned. And so we want to mitigate this. We want to be able to find a way to align the two distributions. And again, a really common approach is to do domain adversarial adaptation, where what we do is we start by learning a classifier to distinguish between features in the source and target domains, and then updating the underlying representation so as to confuse this domain classifier. By doing that, we align the two distributions, making at least in feature space, making the two sources of data indistinguishable. And we've used this for a variety of tasks, such as sim-to-real adaptation for semantic segmentation, where you train on synthetic data like this GTA Grand Theft Auto data set, and then try to evaluate the model in a real-world driving data set like cityscapes. And here, what we did was we applied a domain adversarial objective both in pixel space and in feature space. So in pixel space, that means that you're doing an image-to-image translation task. You're trying to make the images in the from the simulator look more realistic. And once we do that to translate to the cityscapes data set, we get an image that looks like this. And then we can apply that across a variety of images in order to complete our pixel alignment, and then further apply domain adversarial learning on the latent space in order to have our completely adapted model. And we'll apply that on our downstream images, like these real-world images from cityscapes, where the ground truth is shown in the upper right corner. If we were to just train in simulation and deploy our system, you would get the image in the bottom left corner. And here, what we find is that after doing these kind of domain adversarial adaptation, again, this is a marginal statistical alignment technique. And what we find is that things like the road have much improved performance, but also some other artifacts like this person is recognized or this street sign in the background. But overall, the majority of the improvements in algorithms like this are going to be based off of the categories that appear most frequently in the data set, because we are operating using an aggregate alignment technique. So what I mean by that is when you focus your efforts on aligning an entire source distribution, an entire target distribution, this is all of the appearance that occurs inside of these data sets, you're going to be biased towards the really common classes in the distribution. So things like in my driving data set, common classes also means the screen real estate. It also means that because I'm annotating every pixel, it means the objects or the stuff categories that appear very frequently in my image, so things like the road and the buildings in the sky, are going to dominate this particular alignment criteria over things like that street sign in the background. And so actually we find this is that a lot of these alignment techniques that really operate on the marginal statistics are going to over prioritize adaptation to those common classes or to those categories that appear most frequently in the images at the expense maybe of the rarer classes. So we wanted to study this and understand, is there a way in which we can perform adaptation even when we have imbalanced data? So when you have an imbalanced data set, this can occur very naturally in the wild. There's always some classes that are occurring very frequently and some that are occurring less frequently. And when you have a labeled data set, what people might do is they might just manually resample it or use a weighted loss function in order to make sure that the tail classes of your distribution are able to be overcompensated in your learning objectives so that you don't ignore them while you focus solely on the head classes or the really common classes. But when we're talking about an unlabeled data set, you can't necessarily do that same type of resampling. And so what you have is you have potentially a model that was trained on your labeled data set, and whether or not data is naturally distributed with a long tail in the source, you've probably taken some intervention procedures to make sure that it's more balanced during training, so you have a model that works well across all your categories. And now you show up in your test time, appearance has changed a little bit, but you also have a long tail, and now you're trying to figure out how can I adapt between this long tail distribution and maybe a distribution of data that looks a bit different from the source. And so if we want to be able to solve this task of adapting both when we have appearance shift and label distribution shift, taking a marginal statistical alignment technique is not necessarily going to be sufficient because too much has changed between these distributions. And so you don't actually want to align them in that same way. Instead, common approaches to these types of tasks, both in terms of semi-supervised learning and in terms of adaptation, tend to focus more on self-training type procedures. Here's some common recent methods from the DA literature. And importantly, self-training methods, things like entropy minimization, or using pseudo labels and then optimizing with the standard cross-entropy loss. These types of approaches don't require that source and target distribution are equivalent. They just require that you have some amount of signal in the target domain to be able to leverage pseudo labels for further fine-tuning. But they're not perfect. In fact, they struggle a lot, especially in the adaptation scenario. And I'll give you a toy example of why this would happen. So here's, let's say, some objects, circles and triangles, distributed in one data condition. So this is our source domain. We have labels. Because we have labels, we can train a classifier to distinguish between the circles and the triangles. But then the problem arises when we have a domain shift. So this domain shift is going to be defined by the fact that this model that we trained in the source domain is underperforming in this target domain. And underperforming precisely means that some of the circles and triangles lie on the wrong side of a hyperplane that was trained on the source data. So now if we think about what happens with self-training, we're essentially trying to optimize or make the model more confident on its current predictions. So things like entropy minimization really try to take the examples as they're currently labeled and optimize towards becoming more confident in the prediction. If you are taking a triangle and predicting it as a circle, you're going to ask the model to be more confident in its prediction as a circle, and that's an incorrect prediction. And so as a result, what we'll do is you'll have a reinforcing of errors. So all of these examples, however they're already classified, they're going to become more confidently classified, even if it's incorrect. And so what we notice is that when you take these kind of approaches, it's actually a significant limitation if you try to apply a sort of self-training procedure on all observations indiscriminately, because some are correct and some are incorrect. And especially in the case of appearance shift, when we're talking about domain adaptation, there's going to be a lot of incorrect instances. And if we keep optimizing those to have a stronger predictive output, a more confident predictive output, we are going to be reinforcing errors, and we're not necessarily going to be optimizing the objective that we want. So to try to solve this problem, we introduced this algorithm called SENTRY, and this was also presented earlier this week. And SENTRY, very simply, is taking a self-training type of approach to adaptation. But what it's trying to do is it's trying to determine when can self-training be applied, when will it be helpful versus when will it hurt. And we want to take different types of adaptive approaches in those two scenarios. So to be able to predict when an example is deemed to be reliable under a current model, we leverage some existing works in terms of predictive outputs based off of different data augmentations. So one such work that looks at this for adversarial examples applies very simple image transformations and just measures whether or not there's a predictive discrepancy between those outputs. Of course, there's an entire class of literature that uses data augmentations to encode an amount of invariance during learning, like these contrastive learning approaches here. But we're going to use different augmentations as a measure of selective consistency. So we're not necessarily trying to encode invariance to particular augmentations to images. Instead, we're going to use these augmented outputs as a way to identify whether or not instances are reliable. So going back to our toy example, where we have circles and triangles, and we are in this situation where we have these instances that are misaligned. And we'd like to be able, during our transfer learning, to be able to optimize the underlying representation such that we better align these two distributions. And the key idea here is that instead of optimizing some sort of self-training procedure on every single unlabeled target instance, instead, we'd like to be able to determine whether or not an instance is reliable. Reliable meaning that we believe that the classifier from the source is currently performing well at predicting the output on this target instance. And once we've identified those instances, we then just want to optimize only those instances. So ideally, we'd identify these instances that are in fact correctly annotated right now, and only optimize to reinforce the predictive outputs of the reliable instances, such that when we update our underlying representation, we now are aligning all instances on the correct side of the hyperplane. So we're improving our classifier's performance overall. The way that that works altogether is that we start by training a model on our source data set. Our source data is going to have labels. So again, we can train a supervised model, very standard. Now what we're going to do is we're going to take our target instances and we're going to apply this source model to them. So this will give us a predictive output. We'll get some distribution over our categories. Maybe it's correct, maybe it's not. And we want to be able to identify whether or not we think it's correct. So one way to do this is to basically just create augmentations of the image and to pass them all through our model. And once we do that, we have a lot of observations, a lot of predictive outputs. And we can use those predictive outputs to determine whether or not we want to optimize this particular instance. And so for that, we have this selective entropy loss. It takes as input a number of different predictive outputs, applies a consistency checker. That can be something as simple as majority vote or unanimous vote. And if it's consistent, we want to optimize for increasing the confidence on that instance. And if it's inconsistent, we want to reduce the confidence on that instance. So altogether, I don't have time to show you all the results of the paper. If you're interested, it's available on arXiv or in the conference proceedings. But we look at tasks like this MiniImageNet data, or MiniDomainNet data set rather, which does have a distribution shift between its different domains. We train on one domain and then try to adapt to the other domain. We also study more extreme cases in the paper of label shift. But I'll just show you one sample result from the paper. This is an aggregate result averaged across all the 12 shifts in this data set and the 40 classes. If we were to just train on the source model and not adapt, you get about 66%. If you use a distribution matching procedure that doesn't account for label distribution shift, you can sometimes achieve a little bit of improvement, but some methods even hurt performance. Focusing only on label shift and ignoring appearance shift doesn't work as well. Methods that try to do both simultaneously using either a relaxed distribution alignment, some variants of self-training, but using alternative measures of reliability like the confidence of the pseudo labels, or methods that use contrastive learning directly and try to encode invariance throughout training perform a little bit better. And then this approach overall was outperforming the competing baselines on 27 out of the 31 shifts studied, and the other 4 shifts we were just on par with the state of the art. So it's a very simple approach. It's literally just determining when or selecting when to apply a known learning objective, but it already is outperforming a lot of these complex procedures. So overall, what I've talked about today was 2 different but very related ideas. The topic of this workshop is multitask learning. We're all trying to understand whether or not we can train and learn models that are going to be reusable or generalizable across different settings, different tasks. And one step towards that goal is to be able to first understand ways in which our model might fail now. And so for that, we have this benchmark for embodied navigation, understanding how our current systems might degrade in response to different appearance changes before you're learning to solve your embodied navigation task. And we also want to be able to understand how we can reliably reuse components of our model as appearance might change over time. So that's it for this talk today. These are 2 works. Again, they both appeared at this conference earlier this week. I want to thank all the students and collaborators in my lab for their hard work on these projects. And I think we have some time for questions now.
Yes, we do have a few minutes. That's for questions. Yeah, thank you again, Judy, for your very excellent talk. So, are there any questions from the audience? Yeah, before you actually thinking about the questions, so there's actually one small question from the chat. So I will just probably read to you. So you mentioned in this motivating example, you have this dog example that it cannot be recognized by this pre-trained ImageNet model. And this question is about, was this ImageNet pre-trained model pre-trained with this exhaustive data augmentation pipeline, including, for example, motion blur, color jittering, and random cropping?
Yeah, so I'll answer that question, and then I'll also answer what I think is the implication behind that question. So the question itself is just, what was this model? So this was just a model that I downloaded from PyTorch Model Zoo. And I did this example, I ran that a couple of years ago. So it's possible that whatever you would download now might outperform this with additional data augmentation. But that's not really the point. The point is that you don't necessarily have the ability to train on all possible augmentations that you're going to see at test time. So this is something people are actively studying and trying to push the limit of how much variance can we encode in our initial training, and how much does that help with out-of-the-box generalization. And I think that's great and very important. I think we should be trying to improve the robustness of our models out of the box. But even with all of those bells and whistles during training, there's still going to be changes that you see at test time. There's still going to be reasons that you need to incorporate new observations and adapt on the fly, if for no other reason that once you have all of this variety that you're training with, you're not necessarily always going to be optimal at any one particular type of setting. And so you may need to take this general purpose model and specialize it to what you're seeing now.
Yeah, that's great. That's great. Yeah, thanks. So I see are there any more questions from the audience? Yeah, feel free to unmute yourself and ask questions directly, or you can write in the chat. We will read the question. Yes, maybe I can actually use the time to also ask a short question. So for your second work, this domain adaptation to select which sample, let's say you have a consistent prediction, or let's say reliable prediction, so you can reuse them to augment the training set. Have you actually tried to track this? So maybe at the beginning, some of the easy example, anyway, we have consistent prediction, you use them to retrain, but after sometimes the initially hard example also tends to be easy, then we can also have consistent prediction. Do we have this kind of, let's say, the sense of curriculum learning here?
Yep, absolutely. That's what happens, is that we have some plots in the paper. It's probably somewhere in my hidden slides, which I don't know how to access while I'm in presenter mode. But yes, absolutely. We have results that look at what's the set of, like, the distribution of reliable and unreliable samples, and how that changes over time. And what we see is that more samples become reliable over time. So we have a plot that looks at that. We also have breakdown per category to make sure, again, this was particularly designed for this scenario where you might have long tail distributions. So we wanted to make sure that you weren't just over time getting better and better at the common classes and doing nothing for the rare classes. So we have some breakdown of performance via category, and show that there is actually improvement in each category.
Yeah, maybe you can also share with us some more insight about your robustness benchmark, this navigation benchmark. So can we actually also leverage for multitask learning, let's say, to actually render some depths, and not only about recognition, but also have, let's say, depths and normal estimation, or some other like standard like a dense prediction task that can be also used for navigation itself, right? So can you actually maybe share more insight about how this benchmark can be used for, let's say, kind of a multitask learning for dense prediction or this type of task?
Yeah, definitely. So there's already depth integrated, and we're in the process of integrating depth corruptions as well. Right now, the sensor is just a clean sensor for depth. I didn't talk about it today, but in prior work called SplitNet, we looked at a multitask learning objective for these embodied navigation tasks and found that predicting outputs like depth and normals could be used to effectively disentangle some of the visual learning versus the policy learning, and that helped you to be able to transfer faster. So for example, if you added multitask learning as auxiliary losses on top of just the visual encoder, this allowed you that when just appearance changed, you could now use those auxiliary losses, like predicting depth, as an adaptive loss, and just update the visual encoder. And this was much more efficient for adapting this entire pipeline than trying to view new rewards in this new environment and update the entire policy together with the visual encoder. So I think that's the way, or I think that's a pretty interesting direction to look at, to use multitask losses as a way to force the network to encapsulate certain pieces of the pipeline and isolate them in different parts of the model. And I think that if we can do that effectively, if we can kind of create this subtle form of modularity, that will allow us to have much faster transfer and adaptation.